You probably think you know what the Big Bang was, that instant when everything burst forth from nothingness. But the truth is, most of what we've been told isn't quite right. Even physics students eventually realize that the version taught in school only scratches the surface of what scientists actually believe today. When I first began exploring this topic, I wanted to uncover the real story behind the Big Bang and prove the skeptics wrong. But as I went deeper, I found something even more surprising: I was wrong too. Today, many physicists agree that the Big Bang wasn't truly the beginning of the universe. So what was it then? What exactly banged? Was it a singularity, a void, or something far stranger? Let's dive into that question together, but first, forget everything you think you know about the Big Bang. What you're about to hear might completely change how you see the universe. Long before science, people gazed at the stars and wondered where everything came from. Every civilization had its own story. Some believed gods forged the heavens, others thought the universe had no beginning, cycling endlessly through birth and destruction. The Greek atomists believed space and time stretched on forever. The Hindus, Stoics, and Buddhists imagined a cosmos reborn again and again, an eternal rhythm of creation and decay. Then, in 1687, a 44-year-old named Isaac Newton released a book that would change everything, the Principia Mathematica. In it, he revealed that the same laws that make an apple fall also govern the motion of planets and stars. Gravity, he said, was universal. But Newton's insight brought a huge problem. If every particle of matter pulls on every other, then shouldn't the universe collapse under its own gravity? To solve this, Newton borrowed an old Greek idea: what if the universe had no center? If it were infinite and evenly filled with matter, all gravitational forces would balance out. Nothing would collapse. This became our first cosmic model, a static universe, infinite in both space and time. That idea held up for a while. Newton himself believed God may have created the universe, but not necessarily in time. He thought it had always existed, unchanging. But as astronomy advanced, cracks appeared in that perfect picture. When we look into the night sky, we see stars, but we also see vast darkness. If the universe were truly infinite and eternal, every direction should end in a star, and the entire sky should shine as bright as the sun. Yet it doesn't. The darkness meant something profound: the universe couldn't be infinite and static after all. Something fundamental was missing. That missing piece came centuries later from a man who forever changed our view of space and time, Albert Einstein. In 1915, Einstein published his theory of general relativity, and it turned everything we thought we knew about gravity upside down. He discovered that time slows as objects move faster and distances shrink. At the speed of light, time itself stops. Space and time, he showed, are woven together into a single fabric, spacetime. Gravity isn't a mysterious pull between masses, it's the bending of that fabric by energy and matter. The sun curves spacetime, and Earth moves along that curve, what we call orbit. It was a beautiful idea, but it needed proof. In 1919, a total solar eclipse gave scientists their chance. British astronomer Arthur Eddington led 2 expeditions to photograph the eclipse, testing Einstein's prediction that gravity bends starlight. When the results came in, the stars appeared displaced, exactly as Einstein predicted. Overnight, Einstein became a global icon. Headlines read, "Newtonian ideas overthrown." But even Einstein's own equations revealed something unsettling: the universe couldn't stand still. It had to be expanding or contracting. Uncomfortable with that, he added a cosmological constant, a kind of built-in energy in space that could counteract gravity and keep the cosmos stable. Later, he'd call it his biggest blunder, though ironically, modern cosmology brought it back as dark energy. Meanwhile, astronomers were seeing deeper into the cosmos than ever before. For centuries, faint cloudy patches called nebulae puzzled observers. Were they clouds within our galaxy, or entire galaxies themselves? Then came Henrietta Swan Leavitt, one of the underpaid yet brilliant Harvard computers. She studied thousands of variable stars and discovered that the longer a star's brightness cycle, the more luminous it truly was. That meant you could measure a star's distance just by timing its flicker. Using Leavitt's discovery, Edwin Hubble turned his telescope toward the Andromeda Nebula. He found one of those stars, measured it, and made a shocking discovery. Andromeda was nearly 1,000,000 light-years away, far outside the Milky Way. The universe had suddenly grown beyond imagination. Soon after, Vesto Slipher noticed that most galaxies' light was shifted toward red, meaning they were racing away from us. When Hubble plotted their distances against their speeds, he found a clear pattern: the farther away a galaxy was, the faster it moved. The universe wasn't static, it was expanding. The cosmic model of Newton and even Einstein was obsolete. Years earlier, Alexander Friedmann and Georges Lemaitre had already shown through Einstein's equations that an expanding universe must once have been smaller, denser, and hotter. Lemaitre called that early state the primeval atom, a cosmic egg that burst into everything we see today. Ironically, the man who gave birth to the Big Bang idea was also a Catholic priest. Because space and time are inseparable, if space had a beginning, time must have too. Later, Stephen Hawking and Roger Penrose proved mathematically that time really would have stopped at that initial point, a true beginning. But as we'll see, even that idea wouldn't last. The early Big Bang model had problems, though. It suggested the universe was only about 1.8 billion years old, younger than the Earth itself, which we know is over 4.5 billion years. Clearly, something was off. Einstein still disliked the idea of a cosmic explosion. He preferred an eternal, unchanging universe and even suggested that new matter might constantly appear as the universe expanded. That idea didn't quite hold up, but years later, Fred Hoyle, Thomas Gold, and Hermann Bondi revived it as the steady-state theory. Ironically, Hoyle mocked Lemaitre's model on a radio show by calling it One Big Bang, and the name stuck. Still, scientists needed evidence. If the universe really began in a hot, dense state, there should be leftovers from that era. George Gamow and Ralph Alpher predicted that as the young universe cooled, it would leave behind a faint afterglow of radiation. In the 1960s, two scientists at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon a strange hiss in their radio telescope. No matter what they did, it wouldn't go away. When they contacted researchers at Princeton, they learned the truth: they had discovered the cosmic microwave background, the Big Bang's afterglow. It was the proof scientists had been waiting for. NASA's later COBE satellite mapped this radiation in detail, giving us the first image of the early universe. Stephen Hawking called it the discovery of the century. The Big Bang theory now had its smoking gun. But it still left unsolved mysteries, like why the universe looks the same in all directions, the horizon problem, why it's perfectly flat, the flatness problem, and why we don't see certain predicted particles, the monopole problem. Then came a breakthrough: inflation. Physicist Alan Guth proposed that, in the earliest fraction of a second, the universe expanded exponentially, growing faster than light itself. This, cosmic inflation, solved all those puzzles at once. It explained the universe's uniform temperature, its flatness, and even why monopoles are missing. Inflation didn't just fix the math, it also predicted the tiny variations we see in the cosmic microwave background today, the seeds of galaxies and stars. So what actually banged in the Big Bang? According to modern physics, it wasn't matter exploding, it was space itself expanding, driven by a powerful field filled with energy. When inflation ended, that energy transformed into particles and light, creating everything we know. No singularity required. But inflation may never fully end. It could continue in other regions, constantly spawning new, bubble universes, each with its own Big Bang. This is the idea of eternal inflation, suggesting our universe may be just one of many in a vast multiverse. And that's where the science stands today. The Big Bang wasn't an explosion in space, it was the rapid expansion of space. It wasn't the birth of everything from nothing, but a transformation of energy into matter, light, and time itself. We still don't know what came before it, perhaps other universes, other cycles, or something beyond human understanding. But one thing is certain, the more we learn, the more mysterious the cosmos becomes. What began as a single, Big Bang has now become the doorway to infinite possibilities, proof that the story of the universe is far from over.